So, having studied the MLPs and the radial basis function networks, let us see some similarities and differences between these approaches. Similarities: both are nonlinear layered feed forward networks. So, in the case of the RBF, you just have one layer which is a hidden layer, but in the case of MLP you can have multiple layers, but still they are layered networks. They are feed forward because the information flow goes in a feed forward manner from the input layer to the output layer. There is a directivity there and there is no feedback, and they are nonlinear because you have nonlinear activation functions, and the radial basis function has nonlinear elements there. And both of these techniques are universal approximators. That means, given the mapping f from x to y, you can realize this mapping through MLPs and radial basis functions. Now, let us see the differences between these networks. RBF in its basic form has a single hidden layer. This is very important because this is how the RBF is constructed, whereas an MLP has more than one hidden layer. This is an important structural change. But you will ponder at this stage that a single hidden layer is sufficient for universal approximation, right, for both the MLP and the RBF. But why we want several layers in the MLP? Suppose we want to derive context from one layer to the other layer, as in the case of convolution neural networks, etc., then we may have to bring in this notion of layering in the MLPs. So, this is basically a morphological change between the two networks, right. So, RBF has a single hidden layer, whereas an MLP has more than one hidden layer. The second difference, the neuronal model is the same in the case of MLP, that is, every neuron in every layer of the multilayer perceptron has the same activation function, whereas for the RBF each unit, that is the radial basis function unit, can have a different mu depending upon your cluster mean that you can compute and then feed that information into the RBF network. You can have a different mu, but typically from practical standpoint of view we assume the sigma square to be the same for all the units. Okay. And computations in the hidden layer in an MLP requires local gradients, but this is not the case in the case of RBF, right. The way the error flows in the case of MLP is from the output layer through these connections as you update the synaptic weights based on the local gradients, but this is not the case in the case of the RBF because you just have a linear combiner at the output and you optimize in a certain way to choose the weights. Okay. Let us see other differences. For the RBF network, hidden layer is nonlinear, but the output layer is linear. This is an important structural change. Hidden layer is nonlinear, whereas output layer is linear. However, both hidden and output layers of a multilayer perceptron are nonlinear. So, in that sense we can think that MLP has slightly better generalization abilities because the output layer is also endowed with nonlinearities. Okay. Now, the argument of the activation function in a multilayer perceptron involves computing the inner products between the input vector and the weights, right. If you recall, we do this operation phi of W transpose X plus bias. So therefore we have this inner product W transpose X that we implicitly compute. This is not the case in the RBF, because we are looking into the Euclidean norm between the input vector and the mean or the parameter mu j for the jth RBF unit, right. This is for the jth RBF unit. And the last difference, but not the least, is given the same level of network complexity, one can sort of heuristically say that the MLP can provide a better accuracy than the RBF. I mean, this is sort of a question mark that I would like to put. This depends on the data and several conditions. The argument that I would like to give in favor of MLP is, given the output layer also has nonlinear processing elements and it is also nonlinear, we can think of MLP to be slightly better in terms of its generalization abilities given the same network complexity, but this may not be the case. And definitely in terms of the speed, RBF is way faster than the MLP, because RBF you can compute the inverses using the recursive least squares and you can really get computational speed up. Whereas in the case of MLP, if you have several layers, you have to wait to propagate all these errors sequentially through the layers till you reach the synaptic weights connecting the input and the first hidden layer, right. So because of these changes, I would say RBF is certainly faster than the MLP. But the choice of the algorithm really depends upon the data set and the network complexity that you can tolerate. So this can be better studied via experimentation to suit whatever is required in terms of your solution. And particularly if you are implementing these algorithms in hardware, definitely the MLP, there is a certain latency, because you have to compute these elements at every layer, right. The computation has to go through layer by layer. So therefore you have to wait until you cross all the layers till you reach the synaptic weights connecting the input and the first hidden layer. But this may not be the case in the case of RBF, where you can come up with clever ways to realize your hardware. Okay. With this we shall stop here and we will continue with some of the regression estimation problems related to radial basis functions.